All right, okay, here we'll talk about what we know as Carnot engine. And this was uh, developed by Sadi Carnot um, in the 19th century or 1824. Um, all right, okay, so what's this engine? What's the goal? So goal here, as we saw earlier, that the efficiency of a heat engine cannot be 100%, right? So the goal here is what is the maximum efficiency we can get? Our goal is to maximize the thermal efficiency. So here we'll talk about the idealized heat engine, and what I mean is, in an ideal engine all processes are reversible and no wasteful energy transfer occurs due to, say, friction. So it's an idealized case. Okay, um, look at there are 4 cycles here. So here, or this one is the cycle. So in each cycle the QH amount of energy um, is drawn from a hot reservoir at temperature TH, and in the same cycle a QC amount of energy is released to the cold reservoir at temperature um, TC. Imagine the working substance to be a gas confined to an insulating cylinder with a weighted movable piston. The cylinder may be placed at will on either of the 2 thermal reservoirs or on an insulating slab. So here, let's start here. So this is isothermal expansion. So we can put this insulating cylinder at a hot reservoir at temperature TH. So let's say this temperature is TH, and because this is at hot reservoir, and as the gas expands to maintain at isothermal same temperature, the amount of QH flows into the piston. Now, so that is demonstrated from A to B, and during A to B path, QH energy is pulled from the hot reservoir. Then adiabatically, the piston goes from P to C, right? So this is adiabatic expansion. So it's expanded B to C, and it's so quick that adiabatic expansion, there's no transfer of Q. So Q is equal to 0, and this expanding W is positive, right? Then from that step C to D, it is compressed and compressed isothermally. So this is isothermal expansion, and that time it's sitting, let's say sitting at a cold reservoir. This is my cold reservoir, and obviously a heat amount QC is left to the system. And then from D, so when this reaches D to A, it is again adiabatically compressed so that Q is equal to 0, and this negative work is done. So in this circle, an amount during each cycle of the engine, the working substance observes QH amount of heat from a thermal reservoir at temperature TH and discharges QC amount of heat at a constant lower temperature of TC, right? This is my TC. Good. So let's analyze the cycle. So during this cycle from A to B, a positive work is done by the gas, and from B to C another positive work is done. So from A to B and B to C, positive work done by the gas in expanding. So if there is some load on the piston here, that piston will move because of this work. So this is positive work done. And if you want to know how much work is done, then we can calculate the area under this curve ABC. Now we will look at the path CD. In the CD, there is a compressed, so there is a negative work done, and then again D2A is further compressed, and there's a negative work. So if I want to find the work done from C, CDA, then we can find the area under this curve CDA. So net work done is controlled is in the area of this cycle, which is shown here by the pink color. So that's the positive work done, because this is the positive work and this is the negative work. So net work done is is area under the cycle A, B, C, D, and A. So let's look how we can calculate the efficiency of a Carnot engine. So here is shown is temperature on the y-axis and entropy on the x-axis. So this is my TS curve, right? So if you recall the previous slide, so from A to B, this is isothermal expansion, and during that expansion a QH amount of heat is absorbed. When it goes from B to C, that's an adiabatic process, and Q is 0. So change in entropy, because remember the definition, delta S is equal to Q over T, right? So change in entropy here is 0. Same here, we can say that when going from C to D, this is isothermal compression. Then change in entropy is minus QC over T at constant temperature TC, and here again Q0, so there is no change in entropy. So total change in entropy, I can say delta S. So total change in entropy is, if you can say, delta SH, which is here from A to B, right, plus 0, which is from B to C, plus delta S, and let's call it cold. SC cold, from C to D, and from D to A is again is equal to, that's change in entropy there. So we can say this is delta SH plus delta SC, or SL, low temperature, or cold temperature, colder than this is hotter, right? Now if you want to say delta SH is nothing but we took QH at some temperature, and that was T hot, right? Plus this delta SC was QC over TC at constant temperature TC, but QC is leaving, so from the sign convention we see that is minus QC over TC, right? One more thing we know, that if entropy is a state function, right, remember we start here at A, go all the way A, B, C, D, and come back to A, then what do you think about delta S? Since delta S is state property, then delta S must be equal to 0. Recall, delta E internal in a cycle is 0, right? So if we can see that here, we can write, because S is a state property, right? So what does the state property means? It does not depend on the path, it just depends on the initial and final value, right? And for that reason, initial and final is same, so delta S is 0, right? So if I equate this delta S 0 here, then we can say that QH over TH is equal to QC over TC, right? From here, delta S equal to 0, so QH over TS is QC over TC, right? So, and then this will take it to QH over, or let's make it QC over QH is equal to QC over QH is equal to TC over TH, right? So from the previous slide, we know that efficiency we defined as 1 minus QC over QH. So that's what we saw for a heat engine. And this is QC and QH. These are absolute values, right? So this is the value. So sign is already here. So if I go here, then from there we can say the efficiency of a Carnot engine or Carnot cycle, C is for Carnot, is equal to 1 minus TC over TH, right? So that simple term gives us the efficiency or maximum efficiency you can get. And again, we can see here TC, and these all TC and TS are in Kelvin scale, right? Absolute temperature, Kelvin scale. So if you want the TEC, Carnot efficiency, to be maximum, that means 100%, the TC has to be equal to 0, which is impossible. Same thing, higher is the TH value, better it is. But again, it has limitations, because if you go beyond certain temperature, let's say 2000 degree Kelvin or 2500 Kelvin, most of the metals will start melting, right? So again, that has a restriction there, how much um, an idealized engine can get. All right.